Welcome everyone to our X-ray imaging talk with Professor Oleg Shyprko. He's a professor of physics here at UCSD, and he is the vice chair of the physics department. So I'm gonna hand it off to you now. And
thanks everyone. So
yes,
yeah, my name is Oleg. If you guys want to know more about my group, even though the website maybe is not as frequently updated as it used to be, oleg.ucsd.edu, so you just have to know my name. I'm the undergrad vice chair, as Danny mentioned. So if you guys have any issues, any positive things, any negative things about the classes that you're taking, we're trying to, please let me know. Anonymously, there is a portal, or you can just, we can schedule a Zoom if it's something that requires a conversation. So please reach out to me. I really want to know how our major, I assume most of you are physics majors, all of you maybe. So we really want to know how you're doing in classes, and if there is any suggestions about, if there is any, especially during this COVID times, it's hard for the instructors to adjust. So if you feel like somebody's not doing what they're supposed to be doing on the instruction, or if you feel like there could be some improvement, specific improvement suggestions, let me know. Always happy to hear about this. And so today, please interrupt me with questions. You can type them in chat. You can just unmute yourself. I kind of strive on, I want to make it more of a conversation instead of just one-way presentation. But I guess I'm here to tell you about a little bit about my research, but I wanted to tell you who I am first. So I'm condensed matter experimentalist. So we do experiments. Actually, during COVID, I'll explain to you why our experiments kind of slowed down quite a bit, because just like you're going to see Alex Franyo's lab, we are similar to Alex because we do a lot of experiments off-site. So we travel to many locations. We have actually experiment next week in Soleil, France, which we'll do remotely, which is going to be an interesting experience. But we're supposed to be basically there in person. So and basically, my group specializes in X-ray imaging and X-ray scattering in general. So actually, I have this X-ray nanovision as one of the titles of my talk, but sort of a longer version of the title was, let me see if I can, was probing limits of ultra-fast and ultra-small. So I don't know how far we're going to get today in my talk. I want to talk about ultra-small first, and maybe we could talk about ultra-fast in a moment. So this is sort of like, basically, this is a brochure for the UCSD. I don't know if you guys seen this, but roughly speaking, it's hard to sometimes draw the boundaries, but roughly speaking, we have like 5 subgroups. So I'm representing condensed matter experiments. So we basically look at materials at mostly at atomic scale, nanoscale. This is sort of our, if you think about this as length scale sort of problem, we look at materials around you in the world. So we're very different, for example, from astrophysicists. Probably some of you are interested in astrophysics, who look at things that are very far away and looking kind of back into the past most of the time. So that's sort of a very interesting, very important area of research that we have strong representation in our group. And actually, astrophysics actually coupled to high energy in many areas because the origins of the universe kind of overlap in between astrophysics, which looks at very big things, but also high energy physics that technically looks at very tiny things, subatomic particles. But they actually answer similar questions about what is the origins of dark matter, dark energy, how did the universe start, and so forth. Then we have biophysics, and you guys had, I know you had over the summer, you had several talks by David Kleinfeld and Thierry Roy, so you probably know a little bit about this. Is basically the idea that you can apply many of the methods that physicists develop to solve biological problems. In that sense, actually, condensed matter and biophysics is somewhat similar. We just study dead materials, right? We study oxides and metals and semiconductors and things like that, nanostructures, whereas biophysics applies very similar techniques, but mostly looking at live materials. And then we have, I call it plasma physics, but in reality, it's more like it's morphing into what we call atomic and molecular and optical physics very often. And so you probably will hear more about that. That's a smaller group, but still quite prominent. We're actually one of the, sort of, in the old days when it used to be called plasma physics, UCSD is one of the major players in plasma, if you're interested in that research. So just talking about condensed matter. So I don't know if you can recognize some of the names. So Rick Havrit is probably one person you probably recognize. I don't know if I should put a point. See if I can use the pointer, imitate. Usually I don't do this. I don't know if you guys can see this now. So like Rick Averett right here. So he's the SPS advisor, I think still. And I actually used to have the job before him. So on the left, you see experimentalist in red. So we have a number of experimentalists. Alex Rania, I think, is going to do the lab tour. So he actually has somewhat similar research. We'll work a lot together on many projects. So you can see basically some faces and some names. And then you have on the right, you have theory, condensed matter theory. So we have a number of theorists as well working on all basically topics that are of any prominence in the last 10, 20 years or so. So we have a quite vibrant group. I think we actually are the biggest group right now in UCSD physics, condensed matter. I have to count how many people, but I guess 18, no, right? Something like that. So if you're interested in condensed matter, if you, please reach out to some of these folks who are very friendly in general. Why should you study condensed matter? So again, this is kind of my shtick about the things that, unlike, let's say, astrophysicists or high energy or even sometimes plasma, we're actually working on things that are practical that you guys have experience in everyday lives, right? So everybody knows about, if you have a camera in your, everybody has a camera in your cell phone, right? So typically they use something like CMOS or CCD devices to capture the images instead of photographic film. That's actually an invention that came from condensed matter. So that's actually something that was Nobel Prize relatively recently, 12 years ago or so was awarded, even though the development came way back, right, back in the 60s. Similarly, people probably heard about graphene. This is going to be kind of a next generation of new devices that will probably be based on graphene, even though Nobel Prize was already awarded. There is quantum optics, which is another sort of big topic that we have in a number of different folks, primarily Tenya Popinchev and Julia Barreiro works on these topics. And then things like fiber optics, that's what basically makes me being able to talk to you right now is primarily because of things like fiber optics, right? So I can stream myself. So it's both CCD and fiber optics we're using right now to communicate. So imagine the life without all of those, and especially during COVID, it would be quite terrible, right? You couldn't watch Netflix, you couldn't store all the information. GMR, giant magnetic resistance here, that's another Nobel Prize in condensed matter. That's basically the development that allows us to use hard drives and to store information in very small elements of magnetic bits. And to make it small is what basically revolutionized the ability to store information. So most of the information that we have right now in the world is stored on some server somewhere as magnetic bits. So everything, every YouTube video you watched, every Wikipedia search that you've done, all of the stuff that you have is in the cloud, but the cloud is in reality many exabytes of hard drives that are stored somewhere, and it's due to the innovations such as giant magnetic resistance that allows you to read them and write them at very rapid rates and make the bits very small. And there are other inventions. Again, I'm not going to talk about all of them, but I just wanted to kind of inspire people here that in addition to all the many areas of physics where we're looking at fundamental questions like what is the origin of universe, what is the origins of dark matter. In condensed matter, we deal with still very fundamental questions, but all those questions are rooted in some sort of application of technology or something that is actually quite practical at the person's lifetime scale, right? So maybe graphene is not something you have in your phones today, but I can guarantee you that in 20, 30 years, we will see many more applications of graphene, which was discovered just, a little bit, maybe 15 years or so ago. Any questions? I don't know if you guys want to, and again, if anybody has any questions, just interrupt me. Danny and Jillian, just feel free to jump in and interrupt me. So this is kind of, it's maybe
I had a quick question.
Oh yeah, sure, go ahead.
On graphene, is that supposed to be like a silicon replacement in like processors?
Exactly. So basically, and I can talk a little bit more about this. And in fact, Alex Frania is probably going to tell you more. So we haven't, yeah. So the key advantage of graphene is it's basically a highly tunable material that you can change what's known as electron density of states very rapidly by just simply applying relatively small bias. I'm probably using a lot of words that maybe not everybody understands, but the key advantage is, I don't know, so everybody knows that there are materials generally in terms of electric properties divided into metallic and insulators, sort of on extreme ends, right?
Mm-hmm.
Turns out that if you want to make a computer, you don't want to have just something that is always a metal, right? And you don't want to have something that is always an insulator. That's going to be boring. You want to have something that is in between. So that's what semiconductor, sort of in a very simple, 10-second explanation, means, that you can take a material that is somewhere in between. It's not a conductor, it's not an insulator, but by biasing, by applying the voltage, you can kind of make basically something that is switchable, right? So you want to make a switch, right? You don't want to have something that is always allows electrons flow all the time, or something that doesn't allow electron flow at all. You want to have something that you can control. So graphene is one of those materials that is sort of like a next generation semiconductor, but it has huge advantages. And one of them, by the way, is that it's atomically thin, right? So you can think about doing electronics in a very different landscapes. There are other approaches, by the way, and so we lead actually a neuromorphic computing center. So if everybody heard about quantum computing, probably that's the idea that you can encode bits instead of zeros and ones, you can encode them in quantum states. Those of you who've taken quantum mechanics probably have heard about this. This is a very different approach. Neuromorphic computing is a more classical approach. So we're still using zeros and ones in some sense, but we're using the architecture that is similar to our brain. And that's actually something that Alex Franja, myself, Ivan Schuler, Bob Dines, there's 4 people in our department, but actually there's a whole bunch of people from other universities and national labs that are working on. And so that's something I actually haven't prepared a lot of slides on this, but it's something you're probably going to hear from Alex Franja or myself. So that's sort of a separate thing, not based necessarily on graphene. We're exploring other approaches using something called metal insulator transitions. We can take an insulator and turn it into metal and back using light, using temperature, using strain. That's very exciting new sort of approach. But the key idea is that, again, 30-second explanation of what neuromorphic computing is. Your brain is actually much better than most computers at many tasks, right? So recognizing faces is one of them, right? And recognizing, you guys have done all this CAPTCHA, verifications that you're not a robot, right? And the reason why they work is that you can easily identify whatever bicycle or a sidewalk or whatever on one of those annoying pictures, but the computer takes, huge amounts of computing power to identify an image, right? So image recognition is one thing that brain does really well, and that's because of a slightly different architecture, right? It's not the same as in a computer where you have CPU sort of separated from the memory. And so we're actually trying to come up with devices that operate similar to the brain. So that basically the idea is that your brain works on, on the order of 10 watts, 20 watts, so basically like a light bulb type of energy, but it can do tasks that some supercomputers that have megawatts of power cannot really do as well. So that's sort of the general gist, that you can combine, you can create a new architecture where you have neurons and synapses that talk to each other in a way similar to the brain, and create something that is device-based, still lives in the hardware, but can do tasks, much better than current computers can. Anyways, this is a side note, but Tanya, you asked it, so I'm happy to make this into a discussion rather than just straight presentation. Yeah, graphene is something that I think is definitely here to stay. But as you'll see, the main takeaway from all of my talk is that it takes decades, most frequently. Right? If you look at each one of those innovations, right? Fiber optics was in, CCD devices, graphene, all of these things take, decades from the moment of innovation, invention in a sort of fundamental sense, right? We understand the fundamental physics of it fairly well right now, but in order to integrate it into devices takes, in many cases, decades, right? So 10 years, 20 years, 30 years. In case of GMR, giant magnetoresistance, that actually only took maybe 15 to 20 years. That's kind of like almost a record, going from fundamental physics to seeing it in devices that you can buy for reasonable price, right? I have a couple of examples in that. So even if you're not interested in condensed matter physics, I want to kind of give this this message that funding of fundamental science is important for that reason. No company wants to invest into something that takes 20 years or 30 years or 40 years to come to the market, right? So that's where sort of the government funding of all these enterprises is extremely important, especially now. So one example, I just kind of to motivate you guys. So I don't know if you ever think about how fast technology is developing. We see this in our everyday life, including like innovations like vaccine, right? They just came out in record time, and we kind of get used to the fact that the science is moving at an incredibly fast pace. So this is Vatican in 2005, when the Pope, the new Pope was basically inauguration of the new Pope, I guess, in Vatican. And so in 2005, there was one cell phone, like you can see in this picture, right? Somebody took a picture of the crowd with the camera. And this is only, there is one cell phone. And then 2013, only 8 years later, there's a new Pope. And now like everybody has a phone or iPad or something. So it kind of shows you the sort of the rapid, innovation of technology. You guys know this all, right? Hopefully we're probably all used to it, but I just want to give you a couple of examples. So if you think about magnetic recording, again, almost all the data that you guys access right now, right? Including like this talk is being recorded, and what is it going to be? It's going to be somewhere in the cloud, right? It's going to be on the Zoom, or it's going to be on YouTube, whatever. It actually sits physically. If you try to figure out where that cloud is, it's going to be on a hard drive using magnetic recording media of a hard drive. It's not going to be flash drive. It's not going to be. It's going to be in magnetic storage. But magnetic storage has a long history. So the first magnetic recording goes back to 1898, so end of 19th century, where people basically invented it. And then if you fast forward to 1960, right? So again, think about your grandparents or something. So that's the hard drive that they had to unload it on the forklift, right? So you can see the hard drive here. That's basically what the hard drive looks like. It's 5 megabytes, right? So again, 5 megabytes is like one song on your, if you used to have songs on your phone, right? That's basically roughly. And so if you think about like 30 years later in the 80s, that's the first 1 gigabyte hard drive. Actually, if any of you are in Center for Magnetic Recording Research and Recording Media, CMRR, on campus, so we have this. It's basically an engineering quad. But if you can go into the building, you can see it with your own eyes. So this is just a picture of a dog next to the hard drive. So this is 1 gigabyte hard drive. Of course, we all have much more storage nowadays, because basically the size of the bits was shrinking, but it was shrinking, every couple of decades, it would shrink by a factor of 2 or 3. But then all of a sudden it sort of kept accelerating, right? So, and now we have, terabyte drives that kind of, you can buy them relatively cheaply. And so if you think about just all the knowledge that I'm going off on a tangent, this is going to take too long. If you think about all the knowledge that humanity assembled, right? And so if you think about 1986, right? So this is, I know this is probably before most of you were born. Almost all the data was kind of in some form on the print, right? So you could have it on the books, in microfiche or whatever. You could go to libraries and check out the book. And even like in 1993, and even in 2000s, most of the data was still sort of in this analog format, right? So if you wanted to look something up, most of the information was stored in basically on paper or in film or something like that. And it's only recently, it's only the last like 10, 20 years, it's your lifetime where everything switched around. Now everything is digital, right? And the question is, why is it all digital? Well, the reason is that because we have magnetic storage medium. And again, this is something that took, basically over 100 years to get from the point of fundamental invention to the point where we can actually use it at cost, that is relatively small, that we can store all the information that we have in cats playing pianos on YouTube. It's all stored digitally somewhere forever, right? And in the future is going to be even more so, right? So I think we're going to shrink that 6% of all the analog recording. Sorry if it off a little bit. For some reason, my format is different. Everything is going to be digital. And so the reason why all of this is happening, let me kind of zoom out now and kind of tell you about what I do finally, is that we're sort of making huge improvement on pushing the length scales at which we can control materials down to essentially what I call nanoworld. So nanoworld is somewhere here. So if you think about ultra small things that we could make that exist in nature, right? So if you think about, these are orders of magnitude, right? So think about like the width of the human hair, and then you zoom in and there is, red blood cells, and there is virus like corona, even smaller. Ability to control things, and you probably heard from biophysicists, right, that they work a lot in this field, from from looking at DNAs to viruses to cells and so on. But now we actually have technology that enables us to control materials at the same length scale. So basically, we can kind of try to match the nature and make things that are small as virus or even smaller, right? And put them in devices. And that's basically the ability to make and my example is magnetic storage bits that shrunk, or interconnects in your computers that can shrink basically to 10 nanometer-ish scales, means that you can have fast processing, you can have a lot of data storage, you can have all kinds of other magical properties, right? We use materials in our everyday life, from ultralight, carbon bike frames that I use when I go for bike rides and so on. So it's everywhere, including sort of intersection of, let's say, medicine and materials. There is, by the way, there is a gap here in terms of time scales as well, and I want to kind of, I'm not sure if I'm going to have time to talk about this, but if you think about length scales as sort of one frontier, right? So we're sort of fighting this battle of how far can we push down? Can we control individual atoms at some point? Graphene is one example, right? There is a similar battle that is being sort of staged in my field on how fast can we push processes, right? So can we control something on time scales of, sub-nanoseconds? And again, primarily it's driven by some of the technological questions. You want to charge your iPhones faster. You want to have computers that operate faster. But also there is some really fundamental questions that, how fast can you switch a magnetic bit, a spin, right? How quickly can you move electrons, shuttle them back and forth, or ions? And again, it's sort of like, there is a lot of fundamental questions, there are a lot of applied questions. So if some of you are interested in, both sort of this intersection of fundamental and applied, right? So you want to work on something that you will see it, in your lifetime in some sort of devices applications. Condensed matter physics is basically the field that tries to straddle that boundary between applied and very fundamental. Any questions about this at all? So since I know it's super long, but I think I want to make sure that everybody understands something. So that if you just understood like this first 20 minutes, I think you're already that's already great. And then if you don't get what I do in my lab, that's fine. I think that's my main message is this. So so brief short history of X-rays. Some of you probably know X-rays is light, right? It's light, but it's a very short wavelength. The first X-ray image that this guy, this bearded guy, got the Nobel Prize for. That's a picture of his wife's hand. If you think about the X-ray imaging, right? So if anybody broken a hand or had an issue, this is a picture of my postdoc's hand, which is, not that much improvement. Slightly better resolution. My postdoc broke his hand skiing, so I don't know. He volunteered this picture for my talk. So a couple of years ago now. Basically, this is one application of X-rays. You can see through things, right? You can see through bones. So probably the first time you heard about X-rays, it was the idea that you can see, X-rays because of their short wavelengths. They have penetrating power. Mostly it's about penetrating power. We can see if you go to the doctor and, if you go to the dentist, that's what they use it for. However, and probably more important application of X-rays is the fact that because the wavelength is so short, you can diffract from or scatter from atoms. And something that doesn't work with visible light. So visible light wavelength, I'm not going to quiz you guys but if we were in person, I would quiz you. I would ask you, what is the wavelength of visible light? It's on the order of hundreds of nanometers, right? So 500 nanometer-ish, 800 nanometers, depending on the color. But it's hundreds of nanometers or thousands of angstroms. Atoms are on the order of, 3, and so basically nanometer-ish or sub-nanometer, right? So wavelength of visible light is hundreds of atomic sizes. You cannot use the visible light to see atoms for that reason. But X-rays basically can indirectly, they're short. The wavelength is short enough that you can scatter off the atomic planes and so on. So you can basically use them as diffraction grating, which again, if you had this brilliant idea 10 years ago, you could have gotten a whole bunch of Nobel Prizes, because the first Nobel Prizes, after this Nobel Prize, the first Nobel Prize in physics ever for X-rays, there was a whole bunch of Nobel Prizes for physics and chemistry and biology. And so they go on. This, by the way, is my favorite example. I'm not a biologist, but I think that the most important experiment is the discovery of DNA, right? And this is double helix, a diffraction pattern that basically led to the discovery of double helix by Rosalind Franklin and a whole bunch of white guys who stole it from her, right? And it turns out that X-rays actually have been developing quite rapidly in the last couple of decades. And so if you think about Moore's law, everybody knows the Moore's law. So on the left, you see computer speed as a function of year. And so this is basically like sort of how the computing develops. So every every decade we have several doublings of computing speed. So every year, basically, every couple of years, we double computer speed, and that's known as Moore's law. We all know this. So your iPhones in your pocket now have more computing power than supercomputers when your parents were your age, right? But it turns out that in terms of X-rays, if you plot the X-ray sources, this is the first X-ray source. You will see this. Alex Franja will show you some of the X-ray sources that we have in the lab. This is kind of like what we have in the lab, but there are these things called synchrotrons that enable you to have even brighter sources of X-rays. And more recently, we even have something called free electron lasers, which are basically, oops, I think I have auto skip here, which basically allow you to have very, very bright sources. So those developments actually go even faster than the Moore's law. And I wanted to kind of illustrate it because Moore's law is fast already. That's exponential growth of computing power, but computing brightness goes even faster. So what can we do with those X-rays, with very bright sources of X-rays, with X-ray lasers, if you will, right? So my group does, I try to divide this in my head, and these are not exactly representative. So we can look at, I'll show you a couple of examples of each of these. So I can show you a couple of examples, well, maybe one example of magnetic materials that we study in my group. I'll mention it briefly, but we can also, I can also show you a little bit more recent examples of how we can look inside of operating battery, and we can look at basically answer the questions like, how does the battery work? How do the ions go inside of the electrodes at atomic scale? How do they exit? What happens when the battery stops working or works worse, right? We all had this problem that you buy an iPhone or you buy a computer, but over time, the battery sort of doesn't quite charge very well. It turns out that it's kind of a mystery what happens. And so we can actually look inside of the device while it's operating. So I can show you examples there. We work a lot on quantum materials. You'll probably hear again from Alex Franja, if he's the next presenter. Maybe I don't have to talk about too much, but neuromorphic computing idea that I mentioned previously based on this quantum material approach. There is a lot of work that we do on ultra-fast timescales. So these are kind of like sub-nanoseconds, sometimes sub-picosecond timescales where you excite some process and you watch it at very, looking at very short timescales, what happens to the electrons, to the lattice, to spins and so on. And then it's sort of like an offshoot, but there is a kind of almost a weird project where we look at biophotonic materials like butterfly wings. Butterfly wings are actually diffraction gradients. So the colors that you see in butterflies and most birds and beetles and things like that are not pigmentation. They're not real color. It's a color that is created by diffraction gradients. And the nature is actually very clever about how they can engineer this type of very bright colors. And we're trying to understand how we can do this in the lab, but first we have to kind of really understand the structure that nature can provide us. So we're kind of trying to sort of borrow a little bit from Mother Nature and try to figure out how we can duplicate this in the lab. So that's, I probably won't get to the last two topics. Maybe I can cover like first two topics only and answer questions. But if you're interested, we can talk. I'm happy to talk to anybody. By the way, I know now it's weird, right? But I'm gonna offer to anyone. So once we're out of this pandemic, right? So once we're all vaccinated over the by the summer or something like that, next fall, if you guys want to talk about this, just I'll buy you a coffee and we can sit and I'll tell you more about this, right? So anybody who's still on campus next fall, remind me that I offer you this during this talk. Well, let me I don't know. There's all these fundamental questions, but basically, let me show you a couple of examples of where do we do our work, right? So I'm going to keep that slide because that's boring. So we do a lot of our work at various facilities around the world. So both myself, Alex Franja, a couple of other people, Rick Ivory, by the way, he travels to some of these facilities sometimes, even though he has a very nice laser lab in his at UCSD at Mayer Hall. So my group actually does most of the work elsewhere. So this is one of the facilities. If some of you from Northern California, I don't know if you are, if you ever flown to SFO, right, San Francisco Airport, like 5 minutes before you land, you can actually see this. This is the campus of, this is basically Stanford campus, kind of close to Stanford campus, just a little bit west of Stanford campus. And so if you're flying over, you can't miss it. It is like this 3-kilometer, 2-mile long linear accelerator that it was built actually by high energy physicists, and then people like me took it over and basically build, well, help build the first, I didn't build it, but we use it all the time, first X-ray free electron laser. So basically electrons accelerated here, and then we have all the stations here where we do a lot of experiments. So that obviously means that we have to travel to Stanford to do the experiments there. From the inside, it looks like this. It's kind of super long tunnel. So if you keep walking, it goes for miles and miles. This is another facility. This is actually where most of my work has been done. Probably like more than 50% of my work has been done at Argonne National Lab. This is the brightest source of X-rays in terms of synchrotron facilities. Synchrotron meaning like it's a big circle instead of a straight accelerator. But what you can see here, this is 1 mile long. So for scale, you can see the size of the car here, right? And so each one of those modules here inside is a beam, something called beam line, where we do our experiments. So there is, at any given time, there is at least 50 to 80 different experiments going on around here, because we all share the same bunch of electrons that generate X-ray beams. How do we generate them? This is kind of a lesson from electricity and magnetism for you guys. If you take a bunch of electron beam that is relativistic, so these are electrons that are accelerated to 7 giga-electron volts, so basically very close to speed of light, something like 99.99999% of speed of light, and you wiggle it. So you basically have series of magnets, and these are big, large magnets that make the electron beam basically deviate from its direction. And of course, there is Lorentz force that will wiggle it. So if the magnetic field here goes in one direction, and then at the next point it points in opposite direction, you basically creating like a speed bump for electrons. So you're making it accelerate up and down. Each time electron accelerates, it radiates, and it radiates X-rays, and you can make it so that that radiation goes in a very narrow cone, which is what we want. We want to have a very bright source of X-rays. We don't want to have a light bulb. We want to have a laser. And so this is kind of resembles some of that lasing capability, because if you make the beam very narrow and very collimated, it looks very much like laser. So by the way, this is, I don't know, apologize for quality of this picture, but this is an example of such magnet. So it's, in this case, it's 2.5 meters long. Very often we have 2 of those back to back, so 5 meters total. 5 meters is, I have to convert it to feet, but basically it's like 12 feet or something. It's pretty massive thing, and each of these points is a different magnet. So these are quite massive things that create our electric beams. So let me talk about the first example. Let me talk about these magnetic materials. I'm probably going to only talk about the first 2 examples because of time. So we actually can use X-rays to look at magnetic nanostructures in a very high precision. And let me skip the other 2. And the key idea, the 2 different ways that you can do this is, one method is something called full field imaging, or basically microscopy. And this is how basically almost all of the microscopes, all of the optical elements, photographic cameras, your eyes, your eyeglasses or contact lenses work. So basically what you do is you have some sort of optic and you focus it somewhere. So this is your eye. Basically your eye is a lens. In terms of X-rays, it will be like something like a Fresnel dome plate. You can focus it, you can focus your beam, and then you use that, this is the object. We basically illuminate it with a lot of light. And then this will be basically your imaging system. So right now you see me because your eye, which is this lens objective, creates an image of me, right, through your screen, onto your retina, right? So that's basically how the eye works, right? So the idea is that you have an image or an object, you try to put as much light on it as you can, and then, which is the brightness of your LCD screen right now, and then your eye basically demagnifies it on your retina, and that's how you get an image. And so that's how microscopes work. This is how your, any camera works. You basically create an image, you project it on the CD camera or your photographic film or retina, and that's basically imaging. We are doing something different, and that's a very different approach that is quite revolutionary, I would call. Where the key idea is that we let the X-rays diffract to far field, so we have no lenses. So this is basically called lensless imaging. So we eliminate the object and we let it diffract, and what we get in far field means simply that the detector is far enough away, we see something that is a Fourier transform of this object. And it turns out we can solve what is known as phase problem. In other words, we measured, I'll talk about this in a second, but this is actually a fingerprint. This is Fourier transform. You guys probably know about Fourier transform more than most folks that I give this talk to. This is a Fourier transform of this image. You can think of this specific diffraction pattern is intricately related to the configuration, local configuration of domains here. And so by solving for missing phases, I'll mention what I mean by this in a second, we can actually recover this object. And the reason why we're doing this, this is a very complicated way of doing things, is because the X-ray lenses don't work very well. So basically they suffer from all kinds of problems. And I'm not going to talk about that because it's too long. Let me skip through a couple of complicated things. There is basically something called dichroism, where we can see spins. So how do we see magnetism with X-rays? It turns out that you can tune to certain resonant edges. So you can change the energy of X-rays, and by tuning the energy of X-rays to specific wavelengths, we can probe elemental magnetism. So we can see only spins that sit on, let's say in this case, gadolinium or iron or some other element. So that's kind of an important distinction. And the key idea is that if you look at an energy that is arbitrary somewhere else, you see a Fourier transform of a circle. I don't know how. So this is, I'm always struggling with this. I don't know how much some of you have like this intuitive feel for what Fourier transform means. But if you take Fourier transform of a circle, you're going to get Fraunhofer fringes. So this is kind of like a diffraction. Fourier transform of a circle looks like this. If you go in MATLAB or whatever you like, Python code, and just plug in Fourier transform of a circle, you get something like this. It's going to be basically fringing from all these edges of the spherical aperture that we have here. There is nothing interesting going on here. But if you tune to the edge, the specific wavelength, just a couple of 10 eV off, that corresponds to this gadolinium M edge, you begin to see the domains. And so because you have domains, in addition to all these Fraunhofer fringes, you see this, what we call speckle pattern, all these little dots on the, on the higher Q. And that speckle pattern actually encodes the configuration of domains here. So that's basically due to interference of these little things that in Fourier transform become big things in reciprocal space, in Fourier transform space. All right, so I've said a whole bunch of words that probably are confusing. So I want to maybe pause for questions. Does anybody understand what we're talking about? Did I lose you? If I lost you, I apologize, and that's fine. But does everybody know this Alice in Wonderland thing, where things that are small in real space become big in scattering space and vice versa? I don't know. Does anybody want to say something, or this is the time to ask a question, because it's fine if you don't understand this. It's fine. I expect you guys have never seen this before, but.
Yeah, I'm a little confused.
Yeah. What are you confused about?
I think
the whole thing.
Well, yeah, but when you said, I think you said it was fully realized or something, between the difference between the two images. Like
yeah.
why,
So
yeah.
Yeah. So let me kind of try to explain again. So I don't know if. So have you tried to do? I don't know if you've seen like diffraction grading, right? In some of your physics classes, where the idea is that if you have small slit, right, it gives you peaks at larger angles. So the angle is inversely proportional to the size of the slit, right? Another sort of experiment that if you have periodic set of slits, right? If again, like the spacing of the slit between the slits is small, you're gonna have larger angle, and vice versa. If you have separation is larger, you're gonna have a smaller spacing. One experiment that you guys can do at home that I should have prepared, if you have a laser pointer, and you can do this with like any fabric, because fabric has basically a lot of structure. If you shine it through like a t-shirt or something like that, and you try to stretch it, you will see the peaks that will kind of shrink to the smaller angles as you stretching it. So as you make it bigger, the angle will become smaller and vice versa. You can also shine it on your iPhone, because the iPhone has little pixels, and you can actually study the size of your pixels by bouncing your the laser light beam from diffraction gradient that naturally exists on your iPhone. And for example, if you have old iPhone that has bigger pixels, you will see that the peaks are going to be closer together. What I think what your question was maybe related to is basically what I'm trying to tell you is that mathematically this picture is a Fourier transform of that picture. And so normally, if you guys know about math and Fourier transforms, you could say, well, and that kind of leads me to the next question. So if I measured my Fourier transform here, I could just simply do inverse Fourier transform, and I get back to this, right? If there is well-defined relationship, why can I do this? And the answer is that when we measure this, it's known as phase problem. When we measure this image, when we take this image, we only know the amplitudes of the light, but we don't know the phases. Basically, we only know how many photons came into every pixel. We don't know the relative phases between the different parts of the, in this case, X-ray beam. Just like if you take a picture on your phone, you only know that each pixel has been hit with this many photons, but you don't know the relative phases between different photons that came to different pixels. If you did, that would be really cool, right? Because then you can do holography and all kinds of other stuff. But unfortunately, we don't. The phases are lost when we measure the photons. We basically only know the intensities, not the phases, which means that we lost basically the imaginary part of our. So if you think about, we only measured the absolute value, not the real and imaginary part of the phase and the amplitude. I don't know. Most of you have taken 4 series. I don't know if that's. I know some of you are freshmen. I know at least one of you is a freshman. So, so if you're a freshman, I'm not sure if you haven't seen a lot of complex analysis, but basically, let's just assume that what I tell you is true, right? That there is such thing as phases and amplitudes of light, right? Oh, it's like wave, right? So any wave has, you can characterize any wave as both amplitude and phase, right? Everybody knows that. And it turns out that during the measurement of any optical pattern, you typically lose the phases. You don't measure them. You only measure the amplitude. Does that make sense?
We've got one question here in the chat. Simon asks, what's causing the big rectangle overlapping the circle for the diffraction pattern?
Yeah, that's great. So Simon is one of the freshmen here. So that's very good, Simon. I know you from. Yeah, so this is actually something. This is kind of an artifact that we deliberately put in. There is a straight beam. So the beam, I should explain how we did this measurement. But basically, there is a straight beam. So look at this experiment. So we have a straight beam that goes through this magnetic film, and then it basically scatters everywhere. But there is also a direct beam that hits the detector, and the direct beam is very, very powerful. So if you don't block it off, it will burn the hole in your detector. So basically, what we did is we put a thin wire here that we put ourselves to block off the direct beam, because the intensity here is going to be so strong, it will damage the pixels. It will not burn a hole. Actually, maybe I exaggerate, but it will damage that central pixel that will have all of the beam that has not been scattered. So this is kind of an artifact that it turns out we can correct for, but this is just to block off, just to kind of prevent the detector from being damaged, because we have such a strong, powerful activity. It's not important, not super important. Okay, so now we're going to go through the math, and I kind of hate myself for doing this. I know, but basically there is a way to recover the phases, it turns out, and this is the algorithm that we developed in my lab. And I'm going to try to. I know it's maybe very confusing, but one of the challenges but it's important to understand the next step. So basically, what we measure is in Fourier space, and that's an image on the right. The amplitude that I will show using the amplitude is going to be the brightness. So the bright spot is high amplitude. The dark spot is going to be the dark region here would be low amplitude. So we measure the amplitudes, but it's basically black and white image in the sense that because the color, I'm going to use the color to signify the phases. We have not measured the phases. So we only know that some pixels have a lot of light come into it, and some pixels have less light come into it, but we actually don't know the phases at which they come in. So we basically measured the amplitude of the waves, but not their phases. So we only measured half of the picture, basically, as far as I'm concerned, because we would need to know both amplitude and phases to do our mathematical phase, mathematical inverse Fourier transform. So in Fourier transforms, if you take any function, you Fourier transform it, you're going to get a function that has both real and imaginary part, or phase and amplitude. And we lost the phases during the measurement. That's not a phase problem. It's one of the most important it's one of the most important problems in crystallography, and people basically trying to solve structure of proteins and so on. Basically the #1 problem is how to solve the phase problem. It turns out, though, that we can actually solve for the missing phases if we oversample. Okay, there's a whole bunch of words that is going to be. Do you guys know about Nyquist theorem? Has anybody heard of that? Yeah. Okay, so this is those of you who are like engineers or do signal processing. If you measure, maybe I should just skip this, but basically the idea is that if you measure some finite, if you measure something that is a finite length, if you Fourier transform it, you're going to have something in terms of frequency, and it turns out that you don't need to know everything at all infinite range of frequencies. You only need to know it up to 2 pi over that length. So, for example, if let me try to use it using the so the way I learned about it is that if you have a song that is 2 seconds long, and you Fourier transform it, so you broke it down into all different frequency components using Fourier transform, you don't need to sample it at all different frequency. You only need to sample it at 2 pi over 2 seconds, or whatever the duration of the song. And that gives you all the frequency spectrum that you need to have. That's sort of how I learned about this in signal processing. Have anyone heard about this, or is it just kind of blowing your mind? So basically, you don't need, if you have a finite object, you only need to sample it 2 pi over that size, and then you have everything you need to know. It's kind of like basically, there's almost like a matrix analog to this. Like if you have 10 variables, then in reciprocal space, you only need 10 other variables to map it one to one. So I know I'm losing half of you, but basically, let me just kind of let me go to my what I call gibberish talk, right? Which is probably not, but let's see how it's kind of like learning Italian or some language that you don't speak. You only hear like every other word, but then you kind of pick up some words, and maybe you learn something from this. So the key idea is that actually, if you oversample, which means simply that we measured something that is finer resolution than we need to in our detector. So which means that our detector has a lot more pixels than we need. We can actually solve for the missing phases. And the way we do this is that we basically take our Fourier image, we color it randomly with just completely random phases. So we basically put random color or random phase to every single point. Then we do inverse Fourier transform, which is signified here by inverse Fourier transform. We get an object that is actually bigger than what we measured because of this oversampling criteria. If we oversample by a factor of 2, inverse Fourier transform is going to give us a matrix that is actually bigger than our object. And then we know that our object was smaller, so we're going to zero out everything outside of the box that we think it should fit in. In this case, it's the circle. So we're going to make everything outside of circle black because we need, our beam has not measured there. Then we Fourier transform it. Now we have both amplitudes and phases that are shown here that are both wrong. We replace the amplitudes with the ones that we measured from here, and we kind of keep going into this algorithm loop. And it turns out we converge eventually. So we find the missing phases using this iterative algorithm where we start with a random set of phases, and we do this basically series of projections, Fourier transform, inverse Fourier transform, and updating our data to get an image. Let me just show you an example. It's not important if you don't get it. So we get in, basically we started with some random image that some image that I showed you before, the diffraction pattern, and we started with random phases. So, and we're going through this iteration. So this iteration number is how many loops in that algorithm we went through. And at some point, and what is on the right is not important. That's something known as illumination function. That's our X-ray beam profile on the sample. We don't know it. We're actually recovering this at the same time, but that's not super important. What's important is here we begin to see the magnetic domains that were the source of our image. So through this iterative algorithm, we can find the missing phases. And as we're finding these missing phases, we can begin to see the diffraction, the configuration of domains that gave rise to this diffraction pattern emerge. And this is noise because we never measured here, but our algorithm, because of this oversampling, still finds some random zeros in terms of or some random phases here with no intensity. And it turns out that if you do this many, many times, you always get the same image. So the bottom line, the bottom takeaway, if you forget all my gibberish talk about Fourier transforms and Nyquist theorem and all this stuff that you'll learn maybe at some point in upper division or whatever, the key takeaway here is that without any lens, right? We have no lens. We let the light diffract. We lost all the phases, but then we kind of recovered the phases. And by recovering the phases, we formed an image without using any lens at all. Simply using the mathematical relationship between the image and the diffraction pattern. So that's basically solving the phase problem. We formed an image in a computer without using the lens at all. So our computer basically algorithm becomes our lens. And as such, it could be much more perfect than the lens that we could ever make. With X-rays, the lenses are not very well. So this is sort of one type of project, and I know I lost some of you. So that's, but you guys got the flavor for what I do, and it's sometimes difficult to explain everything, and that's why I didn't want to go into the weeds yet. But I don't know, maybe I can pause. Let me give you another example. Maybe that will clear it up. Let me talk to you about how we look inside of the lattice. So this is actually something that I'm really excited about. We are basically, in these experiments, we apply a very similar approach of lensless imaging, but except instead of looking at magnetic domains, we're looking inside of the battery that is operating. We're charging and discharging the battery, and we're looking at where the ions go. So this is kind of an image that is artistic representation of what we're trying to look at. This is lithium ions kind of going in and intercalating themselves into a host material that has in this case it's an oxide that has lithium ions going in and out. That's what happens when all of you guys have done this experiment like this overnight, right? So you charge your phone and you actually do this experiment, except we can actually look inside at basically almost atomic scale and see how this process works out. Okay, so I don't have to tell you again. For some reason my image is very low resolution in my screen, but I'll fix that later. But basically the energy consumption is going through the roof. Everybody knows this, right? And as a result, it's all coupled to the climate. So the question is, can we use renewable energy storage solutions? And almost everything kind of points to the fact that if you want to generate and harvest energy, like my solar panels in my house, if you want to use transportation, which is electrically based, if you want to have electronics like your iPads, your phones, all of this kind of points to the fact that you need batteries, right? So in order to take the energy with you, the electric energy storage solutions are extremely crucial for this, right? And so there was a huge revolution in the last 20 years, and it's still ongoing, about what kind of materials can we use to make sure that cars like Teslas and other electric vehicles, or how to make sure that your iPhones and your computers can hold more charge, that we don't have to replace the batteries as often, and so on. So hopefully I don't have to sell you on the idea that electric energy storage is an important area of research, and that we need more and better materials that can do this in a sustainable way and to help everyone. By the way, this is a paper by Barack Obama in Science magazine that has actually more citations than scientific papers that I get published. Okay, so I don't have to. I already showed you this. Let me kind of tell you what your battery looks like. So if you take, let's say, a battery. So in this case, I'm showing you this coin cell, right? So it's one of those tiny batteries, but basically every battery that you can imagine looks exactly like this. So if you open it up and you stick it under, let's say, electron microscope, you'll see that it's actually made out of a whole bunch of particles, right? So there's a whole bunch of particles that are pressed together. It's a powder. Each of these particles is usually an oxide of some sort. And it's oxide because oxides have large atomic spacing, such that lithium ions, even though lithium is a low Z material, right? It has only 3 electrons. It's actually a very large ion. So the ion has to fit inside of that host material during the discharge process, and then during charge it come out and go into another electrode, which is graphite. So you want to have basically the shuttling of the ions back and forth every time you charge and discharge it. So in some sense, it's a very violent process, because you have this atomic planes where the lithium have to kind of find their home into this host material inside of this complex powder, pressed powder structure, and then find a way out again and do this over and over again every time you charge and discharge. It's something that is very difficult to study, because as you can imagine, this picture was taken by basically extracting one set of particles together and sticking it under microscope. But in reality, this is also enclosed in electrolyte, and there is all kinds of separators and stuff like that. So you could not take this image while the battery is operating, because electron microscopy has to be done in vacuum. You cannot do this. Electrons are very sensitive to any kind of environment. But X-rays can actually see this, maybe not with super high resolution, but with high enough resolution for us, using basically the penetrating power of X-rays. We can go through electrolyte with high energy X-rays. We can hit one of these particles that is oriented the right way, and then we can scatter from this particle. We can see what happens inside of this particle using one of these methods. So again, like this is one of the images of our, looks like gravel or something like that, but it's actually small particles that are sub-micron in size, so hundreds of nanometers. And we can shine in X-rays on them, and this is an experiment that can be done with very, very large beams. And then on the detector, we can see these little dots. Each dot is basically a Bragg peak from one individual particle. They're randomly oriented, so that's why we have different locations on this powder ring here. Each dot basically is a scattering signal from a single particle. And by the way, we're missing a whole bunch of particles that are oriented in a different way. So we only selecting some small number, let's say 50 particles or so, and each one of them gives us a Bragg peak. So as we charge the particle, we basically, what we're doing is we're taking the lithium out of this, lithium ions out of this structure, and that means that the lattice constant, the spacing between atomic planes, will shrink. If you take ions out, it basically will collapse and become smaller, which means that the peak positions will move to the larger angle. So again, this is one of those relationships that the smaller something is in real space, the larger the angle, scattering angle, is going to be in reciprocal space. If you've seen the Bragg law or diffraction gradient law, if you remember diffraction gradient law, the smaller the gradient, the larger the angle, and vice versa. So that's basically what we're looking at. We're looking at changing the atomic spacing as a result of taking lithium out and then putting back in. So that's why it moves one way, and that basically signifies, think of this as 1 over the size of the atomic spacing. And there is a jump, there is a phase transition, which means that the lattice spacing kind of suddenly shrinks. And then it does the opposite when you put the lithium back in. It suddenly opens up, there's a big jump here, and then it slowly keeps opening up. So I know it takes a lot of knowledge to understand this video, but basically the key takeaway is that we can track all these particles while we're charging and discharging a coin cell, and we can look at it basically at atomic level about what happens inside of the battery. And so think of this as kind of like the space in between the atomic planes. So we can do a lot of analysis. We can really understand how this phase transition happens. Phase transition means that there is a sudden jump from one displacement to the next one, and then it goes the opposite direction. I'm exaggerating, but that's kind of the main idea. And this is actually, by the way, one of the reasons why you don't want to discharge your computer completely, or so sorry, let me answer. Jillian, you had a question, right? So the larger something is, the less you need to sample.
Oh, that was old. It's all right.
That's all. Okay. But I should be watching the chat, but it's hard for me to do it both. But basically, we can apply the same idea here. So what we do is we measure. We take a particle, a single particle now. So before I showed you kind of like how it happens with many particles. If you take a single particle, it's now a three-dimensional object. Before I was showing you kind of like almost like a thin film domain, but now we have a three-dimensional object. And what we measure, instead of looking at the particle itself, we measure a Fourier transform, which is basically, it looks like this. It has fringes. If it was a cube, it would look like some weird three-dimensional star or something like that. So we measure this in reciprocal space in a Bragg peak, but it turns out that it has all the information that if you invert it, you're going to get an image of the particle. But you can also see inside of the particle, because we see basically Fourier transform of the whole thing. And even more importantly, so that basically this is like a scan through our Bragg peak. So we see the star right in reciprocal space. We're scanning through it. So these are slices that we're slicing through it on the right side. That's a movie of us moving through this three-dimensional image of reciprocal space. But when you do this whole phase retrieval, let's just say it's magic, right? So I apply my phase retrieval Fourier transform thing where we solve for the phases. You get a three-dimensional image of the particle, except you know everything that is inside of the particle. And the most important thing is you know the phases of the particle, because if you strain the particle, sorry, the phases give us the strain of the particle. This is how much your atomic planes are either squished closer together or pulled further apart. So you have a very sensitive contribution from the strain, because if you think about Bragg law, and again, I don't know how many of you have remembered this or studied this Bragg law, but basically the key idea of Bragg law is that if you have atomic planes, if you phase these two rays, one reflects from the top layer of atoms and the other one reflects from the next layer of atoms, if the phase difference between the lower ray here and the upper ray here is going to be exactly one wavelength, then going in, they're going to be in phase, and going out, they're going to be in phase. So you're going to have a strong interference, and that's called Bragg law, right? It's only true for specific angle that depends on the wavelength and the d-spacing in your lattice. So that's very similar to the gradient, diffraction gradient type calculation. But it turns out if you move those atoms, if you squish them closer together, then now those atoms are not going to be in phase. They're going to be slightly out of phase. Or if you pull them apart, they're going to be out of phase in the opposite direction. So all these phases that we measured, that I had spent a whole 10 minutes talking about phases, right? All these missing phases that we solve for actually are highly sensitive to what's known as strain, how much the atoms deviate from their ideal positions. And so basically by mapping down the strain, so this is one particle and we can see it in 3D, and it's actually hard to show three-dimensional things, but we can see that the strain is actually correlated with where lithium ions are. So when ions go in, they basically push the atoms a little bit further apart. And when you take ion out, it pushes atoms closer together. So all these different colors basically tell you where the lithium ions are. And we can see this in 3D. This is actually maybe better. So this is kind of like if you cut a potato, and we can do this digitally, right? So we didn't actually cut this particle. This particle sits there and operates. The battery works, but we can see at a single particle level, at basically there's the size of a couple of 100 nanometers, we can see that the ions are kind of clustered together here in the red, and there is a much less, almost no ions here in the blue, right? So this is kind of like lithium-rich, lithium-poor regions of our battery. And by looking at how that changes as we cycle the voltage, we can kind of see how the lithium ions migrate through the particle, right? In this three-dimensional representation of slicing it like you would do if you slice the potato. I'm gonna skip a lot of things, but one very important thing, and I'll probably stop after this slide, I promise. One very important thing that kind of bothers a lot of people who study these materials is how do the so-known defects or dislocations form. And so one way that you can introduce a defect in your material, if you think of your material as basically all the atoms are well-defined, periodically structured lattice, right? So this is the atomic lattice of some material. And then somebody decided to insert half of the row of atoms, right into the perfectly. Otherwise, if I took away these purple atoms, it'd be a perfect lattice where everything is normal. But then somebody basically created an additional half row of atoms that is inserted. That's called a dislocation. That's a defect. Sometimes you actually want to have defects because they can strengthen the material. So when you think about something like, I don't know, hardening a sword or a knife, right? So this is blacksmith learned that if you put a lot of defects, you can actually make things stronger. Sometimes it can also make things softer. So again, melting of chocolate, chocolate becomes kind of like if you let it sit in your hand, it becomes kind of malleable where you can kind of deform it very easily. That's because there is a high number of dislocations. Another example is if you take a paper clip, right, and you bend it many times, you basically each time you bend it, you create more and more of these defects like dislocation, and at some point it breaks all of a sudden, right? So it bends the first 20 times, but then 21st time it breaks because you introduce a lot of these defects that can lead to cracking. Turns out we can actually image these dislocations, and I'm sorry that I'm gonna kind of like I said it's one slide, but basically we can see them because if you think about what this defect is, if you told your friend to go around this area, right, there is something weird happens where if you count your steps, if you went 2 steps this way and then 5 steps this way, and then 2 steps this way, 5 steps this way, and then 2 back, instead of coming back to the same location, you're actually going to be 1 off, right? Does everybody understand? So anywhere else, if I went, 3 steps this way, 3 steps this way, 3 steps this way, and whatever, 3 steps that way, I'm back to where I started. But this one is kind of almost like, something weird happens where if you count your steps, you're not going to come back to the same point. You're going to accumulate what I call phase wrap of 1 single step. And it turns out that that's exactly what shows up in our phased reconstructions. Because if you look at your phases as colors, if you go around a certain point here, so 1 point here, the phases will wrap by 1 factor of 2 pi, or factor of 1 unit cell. And if you circle around another point here, you're going to have a phase wrap of another 2 pi, but in opposite direction, by minus 2 pi. What basically it means is that it's, maybe I should stop here. It basically means that it's somebody kind of tore off created a pair of these dislocations, and there's one line here, but then there's another line in opposite direction somewhere else. And so anyways, we can visualize these defects. This is atomic scale defect, right? It's only 1 row of atoms that is basically, it's signified by 1 row of atoms. As far as I'm concerned, it's atomic scale defect. There is this core that is weird core that has 5-fold symmetry instead of 4-fold symmetry. But we can actually see it. We can see it very well with our X-ray imaging technique. And so that's actually extremely important because we're trying to understand how these dislocations form inside of the battery materials, because they're actually they're the culprits that can lead to degradation. So that's one of the reasons why when you charge your iPhone over time, it kind of starts losing the ability to fully charge because basically, maybe I should just stop here. But these are kind of defects that we're studying, and these are very important for all kinds of applications. So maybe I should stop here because I know I exceeded my time, and I know I overloaded you with thinking about Fourier transform. Your brain probably hurts. That's okay. If you don't understand this, that's fine. I gave you basically a graduate level talk, right? So this is the talk I give at the graduate level. So maybe I should pause for questions and I can go back and maybe iterate some of the other stuff.
I have a quick question. How do you add in a row of atoms?
Yeah, so how do you actually don't really add a row of atoms. What you do is you take a row of atoms and you tear it. Let me see if I have a picture on this. Yeah, so if you think about slipping, so if you think about basically removing this row of atoms, but then adding it here, but it's also kind of equivalent to tearing it and shearing it. I don't know if that makes sense.
Okay, yeah, that makes sense.
Right, so in other words, like imagine like cutting through the textbook. Don't do this, please. But if you take your textbook, right, and you cut through every page, and you like move half of the page over, and you tape second page, so the first page of the bottom to the second page top, right? So 2 top and 1 bottom are going to be taped now, right? And then so now you have a half a page left in there, right? And then you kind of and you keep doing this, right? So page 2 is going to be taped to page 3, and bottom, top, and so on. But then in the end, you're going to have a bottom half leaving hanging there. I don't know if that's a good explanation. I never actually used it, right? There's actually 2 ways you can tear it, right? One is kind of shown here. So essentially, what it does is that you're doing something very violent to the row of atoms, where you basically shear them so they kind of skip 1. So basically, this row of atom used to be here, but it's shared by 1. So now you have half of plane of atom hanging here. But then if you move all of them, there's going to be another row of atom that is kind of leaving hanging on the other side. That's one way to shear it. Another way to shear it is like this, right? So you can make basically kind of like a parking lot structure where you shear it all. And so if you go around this page, now you're on the next page, and you can kind of like keep going in a vortex, and it's like a parking lot structure. But then there's going to be another row of atoms kind of missing on the other side. So that's called I don't want to talk too much, but basically there is a screw dislocation, and there is a plane dislocation.
It's super cool. It reminds me of DNA repair.
Yeah, it has probably some topological sort of similarities between all these splits and stuff. See, do I have a better picture? Try to show it. There's lots of images that I have, but maybe I didn't. Anybody else has any questions? I want to make sure that if you guys, I mean, I'm happy to talk about very general question, right? And okay, so Simon is asking a question. Diagram of charges, charge of the battery, the one with blue blobs and blobs with dots. There were blue sections of electron going in and out. What was the section presenting? Is it? Are you talking about this one, blue and Simon? Do you want to clarify? I'm not sure which image you're talking about. It's also blue and red. It's a bit black.
A lot of blue and red. It was a bit back. Oh, I think.
Yeah, skip it. Oh, this one?
Yeah, that one.
Oh, okay. You mean this one? Oh.
No. Yeah, that one right there. The Li plus is going in and out in the corner, and then the electrons going into that blue area. What is that?
Oh, yeah. So basically, you can. Yeah, so basically you need to have, I didn't talk about it too much, but yeah, if you think about how, this is basically a collector for the charges. So when you take, I don't know if I can, I really appreciate the questions, but it's like the full explanation is going to take me like 20 minutes. But basically the idea is that when you take the lithium out of this host material, right, lithium is positively charged, right? So essentially you leave an electron there. So the electron also has to come out, but it goes into a collector. And so that's the collector that provides the current. So when lithium channels back and forth, the electrons are doing sort of the opposite dance, and you want to collect those electrons. Those are the ones that go end up in your wires, right? So the lithium actually never leaves the battery itself, but the electrons are the ones that are leaving, going one way and the other way. Does that make sense?
Yeah, that's a lot better. Thank you.
This is basically a separate part that we didn't address. So there is a cathode, but there's basically like a collector part that collects all the current. So that has to be like a metallic component that collects electrons from the electrolyte solution.
Thank you. Yeah.
It's the battery design. And by the way, there is a lot of people that we work in engineering who are really experts in this field. So this is like my physicist understanding of the batteries, because it's very primitive. But if you talk to them, they're like, oh, actually, what Oleg said is it's even much more complex than that, because yeah, separators and stuff like that. Because you don't want to, for example, you don't want to have this lithium and electron to recombine back, right? Which is what they want to do. So anybody who knows about positive and negative charges, when you separate them, which is what happens in the battery, they want to recombine. And if they recombine, that's a bad thing because that's what leads to explosions of batteries, right? So if you heard about all those Samsung batteries, that's why you can't put the batteries on the plane. You can't, well, not that anybody's flying anymore, but you can't put them in a bag somewhere because they could explode, and then that causes a fire in the plane, and that's kind of bad, right? So everybody heard about this, but that's basically the reason why that could happen is that if this separator doesn't do its job and electrons can recombine with lithium, that means that the energy that you have in the battery is going to be released as a chemical reaction, which is basically this explosion. Not a good thing. So, and again, like engineers, I leave this to engineers to figure that out, right? But we're kind of more interested in fundamental questions of what happens inside of the battery, inside of the electrodes, inside of the cathode, what that leads to, because ultimately, the big picture is that we want to make materials that are safer, but also can store more energy. And those two things are not, and also cheap, right? You cannot make a battery out of something that is platinum or some rare earths, right? So the materials have to be, you're not going to pay $1 million for your laptop, right? It has to be cheap, it has to be easy to make, but it also has to be safe, and it has to store a lot of energy, and ideally it has to be, depends on the application. Some applications you want to have it light, so you want to have a lot of charge per kilogram of weight. So in your phone, right, you want to have a lightweight battery that lasts forever. Also in your phone, you want to have something that you can charge very quickly, right? So there is a lot of ideas. Also in your car, the same idea. You don't want to have a car that weighs 20 tons, right, but holds a lot of charge. You want to have a light vehicle, but can store a lot of energy. But also you want to be able to charge it quickly, right? So one of the sort of dreams is that instead of charging your iPhone battery overnight or your car battery overnight, you can go into the Starbucks, right? And you charge your car, and by the time you get your coffee, 10 minutes later, it's fully charged, right? The same thing with your phone. Everybody wants to charge your phone in 10 minutes, right? So in between classes, you can charge it up and you're good to go for the next day. But some of those things are not compatible. Whereas some other applications, like if I want to have a battery at home that uses my solar, right now it's sunny, right? So the sun is shining, I want to charge it and then discharge it at night when I'm watching Netflix and there is no sun, then I probably don't care about the weight. I can just park it in my garage or whatever. But I do care about the fact that it doesn't explode, right? I don't want to have a fire in my garage because somebody did not engineer it properly. But I don't care. I care much less about the weight. So in those applications, I could have a battery that can weigh, literally a ton. But so what, right? If it's cheap and if it's reliable, and you can hold a lot of charge, that's what I want to have at home. So those applications are very, very different sometimes because they have different requirements.
I have a question. When you fly with a battery, is there enough gamma radiation up in the air to affect the battery?
No, not really. I mean, so yeah. So there is, of course, obviously there is more radiation, X-ray radiation, gamma radiation. Gamma radiation is sort of like an extreme version of X-rays, right? It actually goes through everything, even more than X-rays. So right now, as you guys are sitting, I mean, look it up. Don't quote me, but I'm pretty sure that like as we're talking right now, as I'm saying this sentence, there is like multiple gamma rays that are shooting through me. And then not only they're shooting through me, they're shooting all the way through the earth and coming out of this. And look it up. So don't believe me, but I think it's like every second there is like a gamma ray going through your body right now, which is when I tell non-scientists that, they really get freaked out. But it's okay. It just goes through all of us, and it's actually good that it goes through all of us and doesn't leave any lasting damage. So yeah, so I'm sure that it doesn't really affect it that much. And the X-rays may be a little bit more of a concern, but even then, it's not such a big difference. In general, yes, you do have a little bit more radiation. That's why people who are flying planes, they actually have much higher radiation doses than people like me who use X-rays to study, because we actually have a lot of precautions in all of our X-ray measurements. Experiments are done in kind of hutches, which are well insulated in terms of radiation and stuff like that. We're not next to the battery when these experiments take place. We're actually outside of an enclosure, so we do things, through motorized drivers that kind of manipulate all the samples and stuff like that. But yeah, pilots and flight attendants and so on, they have slightly higher exposure to radiation than normal people, or people even who use X-rays. And by the way, people who take subway every day, they get also slightly higher radiation because the granite and all the underground areas also have sources of radiation as well. So it kind of goes both very high in the sky. But yeah, it doesn't affect the batteries will not explode because of that. The batteries will explode because they either overheat or they malfunction, and basically that's the reason why And you just don't want to have it in overhead, not overhead, whatever, the luggage compartment where nobody can monitor them. And if they start smoking, it just starts a fire and nobody can see it. So overhead compartment is fine because at least you can catch it if something smells. I assume, right? Again, I'm not FAA. I'm not here to advise you on FAA regulations, but I assume that if you have a battery in the overhead compartment like your laptop and it starts smoking, you will smell it and you can do something about it before it really catches fire. Whereas if it's loaded with a whole bunch of other luggage for a 10-hour flight, it's much more of a problem.
Okay.
I actually I didn't come prepared to talk about airline regulations here. So again, like everything I say is not sanctioned officially by any airline companies or whatever.
Well, if we don't have any other questions, then I guess that's pretty much it. Thank you for coming. Thank you for the
thank
talk.
you guys, everyone. And I hope, let me just say something that I know that the last year has been very tough on you guys. I'm really impressed that everybody is resilient and you guys are still pursuing your dreams of physics degrees. Hopefully it's only another quarter or so. But first of all, if you have follow-up questions you're too afraid to ask, if you want to know more about something that I didn't talk about, or just let me know. I'm happy to do the Zoom from my Zoom gel here. But if you if you want to wait until fall, then we can actually meet in person. And either way is fine with me. And again, I promise everybody who reaches out to me, I'll buy you guys a coffee at Art of Espresso or whatever once it's over. Or if you want to talk, I'm home. I'm not doing anything. I'm not traveling. Well, I'm teaching, but doing other stuff. But I'm not going anywhere. So this is actually maybe a good time to approach professors if they want to talk about the research. It's just that joining research groups right now is a bit tricky, and I think some of you probably heard me talk about this. Like right now, the labs are, social distancing is not ideal for being in a lab working close with some grad student or postdoc or faculty because we're supposed to be maintaining very low capacity, right? One person in the lab at a time. So. But it cuts both ways. But at least maybe you can start learning about what people do because everybody's at home. And so if you reach out and say, "Hey, can we talk about your research?" I think a lot of us will say sure, because what else am I going to do? So use that as an opportunity. But hopefully the end is near, right? So hopefully we're going to emerge after this spring quarter and everything's going to be back to normal, or some semblance of normal very soon.
I have a question. Where can we find these recordings?
They will be up on the SPS UCSD YouTube channel. If you are on our mailing list, you should get an email when it's up. And then if you are on our Discord, and we also have a website where we put the recordings. So I'll send the links to those right now.
Thank you.
All right, thank you very much again, and have a nice week 3 of your classes, hopefully.
Thank you, Professor.
Thank you. Thank you everyone for coming. Have a good one.
Bye.